Welcome you all to the Research Spark YouTube channel. So we are running in the unit third of this course, Electromagnetic Theory and Interference, and this is the second part of this unit third. So in this session, we are going to talk on about the rectangular waveguides. So first question is that in the previous we have discussed about the plane waves in the different mediums, and here we are going to talk about the rectangular. So what do you mean by the rectangular waveguides? So first, waveguide is what? So waveguide is simply it has been coined as the some some matters which will carry the wave, that is waveguide. So here as the shape of this particular waveguide is rectangular, so that is why this is called as the rectangular waveguide. One of the good example is your fiber is also an example of the waveguide. Why? Because fiber, optical fiber, is carries the wave in the form of the light. So your optical waveguide, that is your fiber, is a good example of the wave guide. So here we are considering the example of the rectangular waveguide. So since the shape can be any shape, so for the simplicity here we are studying the rectangular waveguides. Okay, so let's come to the point. So how the wave can propagate. So in general, you know, the second order derivative equations, that is in terms of the electric field and in terms of the magnetic field, that is the del square E plus K square ES is equal to 0, and del square HS plus K square HS is equal to 0. So these are the two the equations in the electric field and magnetic field. Further, if you will solve these equations, then you will get the solutions, that is how the electric field and magnetic field is varies, and K is your propagation constant only. So a rectangular waveguide with perfectly conducting walls filled with the lossless materials. So materials may be the different. So now let's try to solve. Actually, here we are trying to solve these these general wave equations that we have derived. That is del square E minus plus of K square E is equal to 0. So let's try to solve, and let's try to find out the values of electric field and values of the magnetic field. That is how electric and magnetic fields will vary inside the rectangular waveguide. So this is our objective. So now question is that how can we achieve the objective? So in order to achieve the objective, we have to solve the uh, second order differential equation in the electric field and magnetic field. So let's try to solve. So first, the equations can be rewritten as del square EZS by del x square plus del square EZ x divided by del square y, and then similarly del square ZS by del Z square plus K square EZS. So here we are differentiating in all the three directions, and suppose the wave is traveling in the Z direction. So now let's in order to solve these long equations, we are for simplicity solving, we are dividing into the three different parts. So we can solve part by part. Okay, so first part, that is x double s x double dash divided by x plus y double dash divided by y. So like that we can make it part, and then we can try to solve. So separately the parts wise equations may be written as x double dash plus k x square plus x is equal to 0, and then particular solution of this will be the the second order. If we will solve the second order differential equation, so x will be the c1 cosine of kx plus c2 sine of kx. So similarly, you can solve all these three equations, and then you will get the solutions. Now further challenge is to find out the constant values, right? The C1, C2 and the C3, C4, C5. So how can we solve these values? So another set of equations, like if you remember the Maxwell third and fourth equations, that is del cross E is equal to minus j omega mu hs, and then del cross H is equal to j omega hs. Now just write one del cross E in the now the on all the domains in all the directions x, y, z, and both the equations, then you will get the set of the 3 and 3 equations. That is total, you will get the 6 equations. Like suppose del using the del cross E, we will get the equation number 1, then equation number 3, and then equation number 5. Similarly, using this del cross HS, we will get the equation number 2nd, 4th, and last one. So in all the directions, like see for del cross E, H mu, J omega mu, H S is like in X direction, in Y direction, and in Z direction. If how can you write the fields? So like that we can write. So what is the advantage? So here now replace the values of the del z square is divided by del z is equal to minus of gamma ezs, and using these previous set of 6 equations, and then we can find out the values of the constant values, and so constant values will be the simply just combine both the equations, and you will get the value something like this, and finally your H square can be written as exactly this one gamma square plus omega square mu, and also it can be written as gamma square plus k square. So exactly to get the values of this gamma, we have targeted to solve that particular equation. Also now this is the much more important one. So h square can be written as gamma square plus k square. Why is it so? Because in order to find out the propagation constant, this is the much more important. And also h square can be written as kx square plus ky square. So these equations will be used in future, that is a propagation constant. So how can you write the values, that is Ez, Ey, Hx, and Hy in terms of the H? So these are the values. Just again similarly, actually here we got the values of Ez, and so using that particular set of equations, similarly you can find out all other sets of the values. So here we got the only two values. Now, what are the different modes of propagation? So, if Ez and Hz both are zero in the suppose in the particular direction, Z direction, then in that case, this is the actually the all those are Ez, like the components of the Ez and the components of Hz, if it is equal to 0 in the wave propagation direction, then this is called the transverse electromagnetic, that is TEM mode. Here electric field and magnetic field both are transverse. Transverse means what exactly? Like suppose both are perpendicular. So suppose if a wave is propagating in the Z direction, then the electric field and magnetic fields may be in the X and Y direction. So that is why this is called transverse. Similarly, what do you mean by the TE mode? So TE mode means electric field is zero in the propagation direction, but magnetic field may not be zero. So that is your transverse TE, that is transverse electromagnetic wave, transverse electric modes. Similarly, another modes, that is TM modes. TM modes means the electric field is not equal to zero, but magnetic field is zero in the propagation of wave of direction. So that is why this is called TM. So very simple. If magnetic field is zero in the propagation direction, then that is called the TM modes. If electric field is zero in the wave propagation direction, that is called TE mode. And if both are zero, then called both mode, means that electric and magnetic both, that is TEM. So whatever is zero in the propagation of wave propagation direction, that is the name of the modes. And if both are not zero, means electric field and magnetic fields both are not zero in the direction of the wave propagation, that is called the HE, that is hybrid mode. So hybrid electric mode. So in this case, neither E or neither H are transverse to the direction of the wave propagation. So they are sometimes referred to as the hybrid. So now if you remember the value of h square in the previous slides that we have derived, then using that only you can derive the values of the gamma, the propagation constant, and then we'll find out the electric field and magnetic field. So like let's consider the case of the transverse magnetic field. So in this case, transverse magnetic field, if you remember the case, then the transverse magnetic field means your electric field should be the zero. And so here these are the boundary conditions. So suppose the rectangular waveguide. So at the rectangular waveguides, Ez is at 0 at y is equal to 0 and y is equal to b. Similarly, Ezx is equal to 0 at x is equal to 0 and x is equal to a. So dimension are x is in the x direction, that is a, and in the y direction dimension of your rectangular waveguide is b. Now h square can be written as kx square plus k square y. Now question is that how can we find out the values of the kx square, ky square? So exactly our target is to find out this value. So how can we find out? So first, the EZ that we have find, that is the solutions, is equal to E naught kx plus ky y to the power minus gamma z. So this is the solutions that we have already obtained in the previous slides. Now since the from the boundary condition, EZ must be 0. So how can you make it 0? So either sinusoidal, this one should be 0, this one should be 0. So how is it possible to make it this one 0? So sine of kx is equal to 0. So only kx a is equal to 0. It will be possible if it is integral multiple of the pi, that is m pi. Similarly, the another term sine kb is equal to 0. So kb is equal to n pi. So now here you can get the values of kx, ky. Once you will get the values of kx and ky, these values just replace it here. Then you will get the value of h square. So h square finally will be the m pi by a whole square plus n pi by b whole square. And gamma is one of the important parameters that will be used now in characterize the different mediums. So you should remember this one. Gamma is what? Kx square plus ky square here minus k square, right? So you must have to remember the values of the gamma. Gamma is nothing. Gamma is alpha plus j beta. So alpha will be here 0 for our case. So case A, suppose cutoff. So your alpha and beta both are 0. In that case, what will happen? Gamma will be also equal to 0, and the equations, that is k square, will be the kx square plus ky square. So that values here, k is equal to, already we have obtained, k is equal to a square root of omega square root of mu e. So omega square mu e will be equal to 0, will be equal to m pi by square plus n pi by square. So here omega you can find, this is also called the cutoff wavelength, cutoff frequency. So this is very much important results. You must remember these values to solve the numerical problems, right? So this is very much important. So case B, that is even a scan, that is no light will propagate, mostly no propagation wave. So here just replace the values. Gamma is equal to alpha and beta is 0. Then you can get these conditions, that is omega square mu e less than equal to this. Similarly for propagation, like your the values, the whatever the k square you are getting, that is omega square mu must be greater than this one, then only your propagation will your wave will propagate in the particular medium. So just replace the values and you can get the values of omega, that is frequency. So here is the propagation constant, that is beta. Here you can replace gamma is equal to j beta, so you will get this value. And so here is the major important point. So the cutoff frequency here, this one you can remember it. So here how will you find out the cutoff frequency? By using this equation. So this is the most important equation that you should remember, or this one. So both are same only. F is equal to twice pi f, omega is equal to twice pi f, right? So this will give you the cutoff frequency. And also similarly you can find out the eta, that is intrinsic impedance, that will be eta dash is equal square root of 1 minus fc by f, and lambda c, that is cutoff wavelength, can also be written as something like this. Also the relation in between the frequency, that is uh, that is frequency is equal to c by lambda. So major thing is to find out the values of the frequency. Here is the summary. So for the two different modes, that is TM modes and TE modes. So mostly both most of the things are same, like cutoff frequency you can use same equations, then your cutoff wavelength and beta, the phase constant, the phase velocity, almost all these important things are same for both. However, definitely the fields, that is electric field and magnetic fields, both will be varying for the both. So just the solutions are very similar to that. You can go ahead and go through the particular. Thank you for listening. And in the next session, we will talk about the fourth unit, that is transmission line theory. However, I have skipped the numerical problems, so you must go to the numerical problems. Because of the time limitations, I am not considering, but if time permits, we'll see some numericals on the rectangular waveguides and the waves in the at the end of the session. Thank you.